Hello my friends and welcome back to the You Can Do TV channel. This is RC80 Comprehensive Monitoring Double Axle Friction Welding Machine manufactured by Jiangsu Raicheng Machinery, China. The machine is designed and manufactured by drawing on the advanced design concepts. It adopts a unique inner and outer double body structure to release more operating space. The new bridge clamping and positioning device ensure accurate positioning during welding. High-quality hydraulic drive system provides more stable power. A comprehensive monitoring system, monitor, record and store welding data, which are easily been read. This video is about submerged arc welding at Arc Energy Resources Limited in Gloucestershire, UK. Submerged arc welding, SAW, is a joining process that involves the formation of an electric arc between a continuously fed electrode and the workpiece to be welded. A blanket of powdered flux surrounds and covers the arc and, when molten, provides electrical conduction between the metal to be joined and the electrode. It also generates a protective gas shield and a slag, all of which protects the weld zone. Submerged arc welding is viewed as a high productivity process and is usually automated, mechanized in its form. The simplest application of the process uses a single wire. This welding process is typically suited to the longitudinal and circumferential butt welds required in the manufacture of pressure vessels, and for joining plating and stiffeners in shipyards. Welding is positionally restricted and is normally carried out in the flat or horizontal positions because of the highly fluid weld pool, the molten slag, and the need to maintain a flux covering over the arc. In the grand scheme of maritime logistics, the weight of a shiploader may seem like a mere statistic. However, in the world of heavy industry and port operations, every ton matters. A shiploader, an essential component in port infrastructure, facilitates the efficient loading of bulk materials such as coal, grain, ores, or cement onto vessels, ensuring smooth maritime trade operations. The weight of a shiploader is a critical factor in its design, construction, and installation. For a project in the USA, manufacturing the steel construction of the ship unloader is a meticulous process that demands precision and expertise. The steel construction serves as the backbone of the ship unloader, providing the necessary structural integrity to withstand the rigors of continuous operation in a maritime environment. To ensure the structural integrity and stability of the ship unloader, attention is paid to every detail in the manufacturing process. High-quality steel, known for its strength and durability, is selected for the construction, meeting stringent industry standards and regulatory requirements. Advanced engineering techniques are employed to optimize the design, minimizing weight without compromising structural integrity. In the manufacturing facility, skilled craftsmen and engineers meticulously fabricate and assemble the steel components of the ship unloader. Precision cutting, welding, and machining techniques are employed to ensure the accuracy and reliability of each component. Quality control measures are implemented at every stage of the manufacturing process to detect and rectify any defects or imperfections, ensuring that the final product meets the highest standards of quality and performance. Once the steel construction is completed, it undergoes final inspection and testing to verify its structural integrity and functionality. Electrical, hydraulic, lubrication, and water installations are meticulously integrated into the steel structure, ensuring seamless operation and optimal performance. The ship unloader is then transported to the assembly department in Szczecin, where it undergoes final constructional and mechanical assembly into a complete device. During the assembly process, experienced technicians and engineers oversee the integration of various components, ensuring proper alignment and functionality. No load commissioning is conducted to test the performance of the ship unloader under simulated operating conditions, verifying its functionality and reliability. After rigorous testing and inspection, the ship unloader is loaded onto a pontoon for transportation to its final destination. Internal transportation logistics are carefully coordinated to ensure the safe and efficient loading of the ship unloader onto the pontoon. Once on board, the ship unloader is ready for deployment, poised to enhance the efficiency and productivity of port operations, facilitating the seamless loading of bulk materials onto vessels and supporting global maritime trade. The 76mm pipe 60x60 profile production line is a sophisticated industrial setup designed to manufacture pipes and profiles with specific dimensions and properties. Here's how it works. Raw material feeding. The process starts with the introduction of raw materials, steel coils, into the production line. These materials are fed into the line through rollers. Forming. In the forming stage, the raw material is shaped into the desired profile. For a 60x60 profile, the material passes through a series of rollers and dies that gradually bend and shape it into the required tube profile. Welding. The formed profile undergo welding to join the edges and create a continuous pipe. Sizing and straightening. After welding, the pipe undergoes sizing to ensure its dimensions meet the required specifications. Additionally, it passes through straightening machines to correct any deformations and ensure the pipe is straight and uniform. Cutting and finishing. Finally, the pipe is cut to the desired length and subjected to finishing processes such as deburring, coating, or surface treatment to enhance its appearance and performance. Welders are installing thermite welding equipment to weld railway track. The railroad thermite welding is regarded as the most high-efficiency method to weld railroad tracks. This method gives the high efficiency, reliable quality, and high adaptability. So, the railroad thermite welding becomes the most popular way in railroad construction.
Building a custom 16-foot welded aluminum boat is a complex process that involves a lot of planning, skill, and attention to detail. Every aspect of the boat, from its size and shape to the materials used in its construction, must be carefully considered to ensure that the final product meets the client's requirements. The first step in building a custom aluminum boat is to create a detailed design that takes into account the boat's intended use, weight capacity, and other important factors. This design may be created using computer-aided design (CAD) software, or it may be drawn by hand on paper. Once the design is complete, the fabrication process can begin. This typically involves cutting the various pieces of aluminum that will make up the boat's hull, deck, and other components. These pieces are then welded together using a combination of Mig, metal inert gas, and Tig, tungsten inert gas, welding techniques. One of the most important components of any boat is the transom, which is the vertical surface at the rear of the boat that supports the engine. In the case of a 16-foot welded aluminum boat, the transom is typically made from 1/4 thick aluminum, which provides the necessary strength and durability to support the weight of the engine. The hull bottom of the boat is also a critical component that must be carefully constructed. In a 16-foot welded aluminum boat, the hull bottom is typically made from 3/16 thick aluminum, which provides a strong, durable surface that can withstand the impact of waves and other obstacles in the water. The sides, deck, and console of the boat are typically made from 1/8 thick aluminum, which provides a lightweight yet sturdy surface that is easy to work with and can withstand the elements. When building a welded aluminum boat, there are several important considerations that must be taken into account to ensure that the final product is safe, durable, and effective for its intended use. Here are a few key notes to keep in mind. Use high-quality materials. Aluminum is an excellent material for boat construction, but not all aluminum is created equal. Be sure to use marine-grade aluminum, such as 5052 or 5083, which is specifically designed for use in harsh marine environments. Ensure proper welding techniques. Welding is a critical part of the boat building process, and it's important to use the proper welding techniques to ensure that the boat is strong and watertight. Mig and Tig welding are two common techniques used in aluminum boat building, and it's important to use a skilled and experienced welder to ensure that the welds are strong and durable. Follow a detailed design plan. Building a boat without a detailed design plan can lead to mistakes, errors, and inconsistencies that can compromise the safety and performance of the boat. Be sure to create a detailed design plan that takes into account all of the necessary components, materials, and specifications for the boat. Choose the right thickness for each component. The thickness of the aluminum used for each component of the boat, such as the transom, hull bottom, sides, deck, and console, will depend on the intended use of the boat and the expected conditions it will face. Be sure to choose the right thickness for each component to ensure that the boat is strong and durable. Consider the weight distribution. Proper weight distribution is important for the safety and performance of the boat. Be sure to consider the weight of the engine, fuel tanks, batteries, and other components when designing and building the boat. Test the boat before use. Once the boat is completed, be sure to test it thoroughly before taking it out on the water. This will help identify any issues or problems that need to be addressed before the boat is put into regular use. Once all of the components of the boat have been fabricated and welded together, the boat can be painted or coated with a protective finish to ensure that it remains in good condition for years to come. Finally, the boat is outfitted with any necessary accessories, such as a self-bailing center console, navigation lights, and a Honda 50 horsepower engine that can propel the boat to a top speed of 30 knots.
A spoolbase is a shore-based facility used to facilitate continuous pipe laying for offshore oil and gas production. The facility allows the welding of single or double joints, 40 or 80 feet of steel pipe of 4 inches to 18 inches diameter, into predetermined lengths for spooling onto a reel lay vessel. The Clue's MIG narrow gap technology offers a particular economic efficiency for welding thick-walled component parts. In comparison to the conventional weld seam preparation, the weld seam volume can be reduced by about 60%. The rectangular narrow gap blade with a length of up to 400 millimeters, which guides the wire electrode, the shielding gas, and the cooling water. The weld seams with the typical constant seam structure meet the highest quality demands. In the tandem weld process, 2 arcs burn in a common molten pool. Tandem weld is characterized by 2 electrically separated processes which match each other perfectly. This possibility opens up a multitude of combinations. The front wire ensures a safe penetration. The back wire quickly fills big joints with filler material. The high deposition rate results in weld speed and in volume filling. Therefore, tandem weld is suitable for thin and for thick plates.
Welding quality check. Point number 1. Point number 2.
Audi Hungary is one of the companies with the largest turnover and export in Hungary, producing 2 million engines and 135,000 cars in 2014, assisted by FANUC industrial robots at its production facility. FANUC robots are typically used to improve productivity, product quality, cycle times, and the overall efficiency of a manufacturing process. There are many different applications that FANUC robots can be used for across numerous industries. One of the popular applications is welding. FANUC robots are capable of automating arc, spot, and laser welding, among many other welding processes. FANUC's arc and spot welding robots are frequently used in the automotive, oil and gas, and aerospace industries. FANUC welding robots produce durable, high-quality welds which are crucial to the items manufactured in these industries. The FANUC ArcMate 120 IC is a popular FANUC robot for welding automation. Linear friction welding, LFW, is an established niche technology applied by world-leading gas turbine aircraft engine manufacturers to fabricate bladed disc, blisk, assemblies. The main challenges are associated with the surface area that can be welded, due to the high forces required and the control of welding parameters to ensure accuracy of the finished part. Steel pipe, using the Submerged Arc Welding process, SAW, is manufactured by Hall Longmore to a diameter ranging from 660 mm to 2,540 mm. Steel pipes are fabricated from steel plate bent to a circular form, or they may be continuously produced from a coil of steel strip bent to a spiral and butt welded along the spiral seam. Joints between coil ends of spiral welded pipes are known as scalp end welds. Butt welded pipes are made from rolled strip with a longitudinal seam furnace butt welded by a continuous process.
Point number 2.
A hot spinning machine utilizes the process of hot spinning to shape metal components. Firstly, a piece of metal is placed onto a lathe. Then, a torch is employed to heat the metal to a high temperature. As the metal spins on the lathe, a tool presses against the heated surface, causing it to distort and take on the desired shape. This process is particularly effective for shaping metals like aluminum, steel, and copper into intricate and precise forms. In the bottom closing operation, the hot spinning machine is used to shape the bottom portion of the metal component, while in the neck forming operation, it is employed to shape the neck or upper section. These operations allow for the creation of various parts and components used in industries such as automotive, aerospace, and manufacturing, where precision and strength are paramount. Pipeline welding, particularly within the realm of the United Association Pipeline Local 798, is not just a job, it's a way of life. The document paints a vivid picture of the dedication, pride, and skill embodied by those who work in this elite profession. From the onset, it's clear that pipeline welders are a breed apart. They're described as the elite among quality laborers, with a tradition that stretches back to monumental projects like the Big Inch and the Alyeska pipeline. Their work isn't confined to comfortable environments. They face the extremes of weather and terrain, from blistering heat to bone-numbing cold, from snowstorms to high winds. Yet, regardless of conditions, they never compromise on the quality and craftsmanship of their work. Pipeline welding isn't for everyone, but for those who choose this career, it's a source of pride and fulfillment. It's hard work, but it's honest work, and there's a deep satisfaction in knowing that you've earned your paycheck through your labor. It's a career that's passed down through families and local unions, with training often occurring on the job, in the field, or at elite welding schools like the one in Tulsa. What sets pipeline welders apart is not just their skill with a torch or their ability to endure harsh conditions. It's their unwavering dedication to their craft. They take pride in their workmanship, knowing that each weld they make contributes to the reliability and safety of the pipelines that transport oil and gas across the continent. Moreover, there's a sense of mission among pipeline welders. They recognize the importance of their work in ensuring North America's energy independence. With a 100-year supply of natural gas available, the need for pipelines to transport this valuable resource is greater than ever. And it's the pipeline welders of Local 798 who are uniquely positioned to meet this need. In the end, being a pipeline welder isn't just about the paycheck or the prestige. It's about something deeper, something that swells up in your chest and fills your whole soul. It's about knowing that you're one of the best, part of a select group of skilled professionals who get the job done right, every time. It's about being tough, determined, skilled, hardworking, and fearless, the qualities that define a 798 pipeliner. The production process of built-up H-beam begins with dimension inspection, where every aspect of the raw materials is scrutinized to meet the specified requirements. This inspection ensures that the beams are manufactured to precise measurements, crucial for their intended use in construction projects. Following dimension inspection, the plate cutting process takes place. Each plate is measured and assigned a unique part number for traceability purposes. This step ensures that the materials are accurately prepared for the assembly process that follows. During assembly, the individual components are joined together to form the H-beam structure. This assembly process requires precision and attention to detail to ensure that the final product meets the required specifications. Submerged arc welding is employed to bond the components together. Welding parameters such as current and voltage are set according to approved welding procedure specifications to achieve strong and durable welds. Once the welding process is completed, the beams undergo a straightening process to correct any flange distortions. This mechanical correction ensures that the beams are perfectly aligned and ready for the next stage of production. Dimension inspection continues throughout the production process, with visual, ultrasonic, magnetic particle, and dye-penetrant testing methods employed to detect any defects or irregularities. After the fitting process is completed by qualified fitters and welders, the beams undergo a thorough cleaning process. Rust is removed using an automatic shot blasting machine, leaving the surface clean and ready for further treatment. Surface roughness inspection ensures that the surface meets the required standards before proceeding to the painting process. Coating thickness inspection is carried out to verify that the paint coating meets the specified thickness requirements. Once all quality checks are completed, the finished goods are ready for delivery to customers. Apogee robotic welding revolutionizes the welding process for excavator buckets, traditionally a labor-intensive task. With its streamlined approach, the complexities of robotic welding are simplified into 3 straightforward steps. Step 1 involves selecting the welds and defining the welding parameters. Next, in Step 2, the part undergoes scanning. This step utilizes advanced technology to accurately map the surface, providing essential data for the welding process. Finally, Step 3 executes the welding itself. With Apogee's robotic system, this phase is seamlessly integrated and automated, minimizing errors and maximizing productivity. Traditionally, robotic welding for excavator buckets posed significant challenges. The uniqueness of each bucket necessitated extensive programming, and the complexities of synchronizing the robot and positioner added further complications. Moreover, deviations occurring after metal bending added another layer of difficulty. However, Abigy's innovative approach transforms this arduous task into a simple and efficient process. By eliminating the need for manual programming, the system drastically reduces setup time and increases overall efficiency. With Abigy, robotic welding for excavator buckets becomes accessible and hassle-free, empowering manufacturers to enhance productivity and quality without compromising on complexity. Structural steel fabrication is a multifaceted process that encompasses several intricate stages, employing specialized equipment and highly skilled personnel to transform raw materials into meticulously crafted structural components essential for diverse construction projects. At SteelFab, a renowned structural steel fabricator, the fabrication process is meticulously overseen to ensure unwavering standards of quality and precision are maintained throughout. Commencing with the receiving of raw materials, steel shipments arrive at the facilities aboard semi-trucks, where they are carefully unloaded and strategically positioned within the yard. Prior to commencing fabrication, a meticulous inspection of the steel is conducted to ascertain adherence to stringent quality benchmarks. Upon material approval, it proceeds to the shapes department, the hub of advanced CNC, computer numerical control, machinery. Here, a spectrum of sophisticated equipment is deployed to execute precise cutting, drilling, punching, shearing, and burning operations in accordance with exacting specifications. The state-of-the-art facilities boast innovative machinery capable of processing up to 2,000 tons of material weekly. In the realm of plate fabrication, the utilization of cutting-edge plasma and oxy-fuel cutting machines facilitates the precise shaping of complex geometries and the drilling of holes with utmost accuracy. Furthermore, simpler shapes are sheared using wide shears and subsequently bent utilizing press brakes to yield an array of diverse components. The fabrication of beams, columns, channels, tubing, and pipe is orchestrated within dedicated sections of the facilities, housing beam lines replete with an arsenal of saws, drills, copers, cambering machines, and ancillary equipment essential for handling various materials. Each individual piece undergoes meticulous scrutiny to ensure compliance with dimensional tolerances and rigorous quality criteria. The assembly and fabrication phase are entrusted to a depth team, tasked with transposing intricate dimensional data from blueprints onto the physical steel components. Heavy fabrication is conducted within specialized workshops equipped to accommodate assemblies weighing up to 120,000 pounds. Robotic-controlled submerged arc welding machines are employed to execute precise and efficient welds, ensuring structural integrity. In addition to structural steel, the facilities specialize in the fabrication of miscellaneous steel products, including stairs, handrails, and ladders. These custom-designed assemblies are crafted from an assortment of materials, including stainless steel, brass, and aluminum, catering to diverse project requirements. Adherence to stringent quality control protocols is paramount throughout the fabrication process. The team of certified welding inspectors meticulously scrutinizes all welds, with ultrasonic and magnetic particle inspections conducted as necessitated to detect any imperfections. Coatings play a pivotal role in safeguarding fabricated steel against corrosion and environmental degradation. The coatings department is equipped with cutting-edge technology to apply a diverse range of coating systems, ranging from standard shop paint to intricate zinc-based coatings. Upon completion of fabrication, the finished material undergoes meticulous preparation for shipping. Barcoding systems are employed to meticulously track production and generate accurate shipping tickets, ensuring seamless logistical operations. Tablets afford fabrication personnel real-time access to drawings and revisions, minimizing errors and downtime. The edge banding machine designed for manufacturing tops for sheets up to 3.75 mm thick is a versatile and robust piece of industrial equipment. Its core components and capabilities can be described as follows. The machine is equipped with a 2-horsepower motor coupled with a reducer. This combination provides the necessary power to drive the edge banding process. The motor is connected to the machine's mechanisms through a straight chain connection, ensuring reliable and precise operation. This edge banding machine is suitable for processing sheets made of both stainless steel and carbon steel. It can efficiently work with sheets up to 3.25 mm thick for stainless steel and up to 3.75 mm thick for carbon steel. The built-in especially sheets accommodate materials ranging from 5 mm to 25 mm in thickness, further enhancing its versatility. The machine's axles are designed with gear traction and heavy-duty bearings to withstand the mechanical stresses of the operation. A set of pulleys, made from tool steel and heat-treated, ensures smooth and precise sheet movement during the edge banding process. The machine features an adjustable support arm made of durable tube material, allowing for customization to suit the specific workpiece. Guides with adjustable settings and a choice of nylon or steel spools provide support for the sheet being worked on, ensuring stability and accuracy. The machine is equipped with an electrical control system that incorporates safety relays. This ensures the operator's safety and helps prevent accidents during operation. The machine's exterior is coated with synthetic enamel paint, providing protection against corrosion and enhancing its aesthetic appeal. This edge banding machine offers flexibility in terms of the parts it can process. It can work with a minimum part radius of 150 mm and a maximum part radius of 3,000 mm. It is suitable for handling conical and flat pieces with edge angles of up to 100 degrees. Head forming is a critical process in the fabrication of pressure vessels, such as boilers and tanks. These vessel heads, typically made of materials like steel or aluminum, play a vital role in containing and maintaining internal pressure safely. The head forming process involves shaping flat plates into curved or domed configurations, ensuring they meet specific design requirements and safety standards. Common methods include cold forming, hot forming, and spinning. Cold forming uses hydraulic or mechanical presses to bend the material, while hot forming involves heating the material to make it more pliable. Spinning employs a lathe-like machine to spin and shape the material into the desired contour.
Shearing. The first step in the manufacturing process is shearing. In this step, raw material in the form of steel bars is cut into specific lengths required for the production of combination wrenches. This process is carried out with the help of a shearing machine. Shot blasting. The next step is shot blasting. In this step, the cut steel bars are cleaned and prepared for forging by blasting them with abrasive materials such as steel shots or grits. Forging. The third step is forging. In this step, the prepared steel bars are heated in a furnace to a specific temperature and then shaped into the desired form using a forging press. The forging process compresses the steel, making it stronger and more durable. The steel bars are heated to 1250 degrees centigrade to prepare them for the hot rolling process. Hot rolling. In this step, the heated wrench blanks are fed through a series of rollers that reduce their thickness to the required dimensions. The hot rolling process involves feeding the heated metal strip or sheet into a set of rollers that apply pressure to reduce its thickness. The temperature and pressure of the rollers are carefully controlled to ensure the metal is not overworked or damaged during the process. The hot rolling process can be repeated multiple times to achieve the desired thickness and mechanical properties. Cooling. The forged wrench blanks are then cooled to room temperature to prevent any warping or distortion caused by the high temperatures used in the earlier steps. Blanking. In this step, the cooled wrench blanks are cut into individual wrenches with the help of a blanking press. Sandblasting. After blanking, the individual wrenches are cleaned and prepared for further processing by sandblasting. This step removes any remaining rust, dirt, or other impurities present on the wrenches. Grinding is a critical process for achieving the precise dimensions and smooth surface finish required for the wrenches. After the wrenches are blanked, they are sent through a grinding machine that removes any rough edges and surfaces. The grinding process is automated and controlled by computer programs to ensure consistency in the finished product. Tumbling. In this step, the sandblasted wrenches are placed in a tumbler with abrasive media such as ceramic chips or steel pins. Tumbling smooths and polishes the surface of the wrenches, removing any sharp edges or burrs and improving their appearance. Coining. The next step is coining. In this step, the combination wrenches are pressed into a die to create the final shape and surface texture. Coining further improves the strength and durability of the wrenches by increasing their density. Drilling. In this step, the combination wrenches are drilled with the appropriate size holes to accommodate bolts and nuts of various sizes. Broaching. After drilling, the combination wrenches are broached to create the characteristic square openings required for fitting onto bolts and nuts. Tumbling. The combination wrenches are once again placed in a tumbler to remove any remaining burrs or rough edges caused by the broaching process. After that, the wrenches are sent through a heat treatment process. Heat treatment involves subjecting the wrenches to extreme temperatures to alter their physical and mechanical properties. In the case of beta tools combination wrenches, the heat treatment process involves hardening and tempering the wrenches to increase their durability and strength. The heat treatment process begins with heating the wrenches to a temperature of around 860 degrees Celsius, at which point the steel undergoes a transformation called austenitization. The wrenches are then quenched in a bath of oil or water to rapidly cool them and transform the austenite into martensite, a hard, crystalline structure. After quenching, the wrenches are tempered by reheating them to a temperature of around 560 degrees Celsius. The tempering process allows the martensite to transform into tempered martensite, which is stronger and more ductile than the untempered martensite. Polishing. In this step, the combination wrenches are polished to give them a final glossy appearance. Nickel chrome plating. The final step in the manufacturing process is nickel chrome plating. In this step, the combination wrenches are electroplated with a layer of nickel and then a layer of chrome to provide a durable and corrosion-resistant surface finish. Checking and inspection play a crucial role in the beta tools combination wrench manufacturing process. Quality control measures are taken at every step of the process to ensure that the final product meets the required specifications and standards. Various inspection and testing techniques are employed to detect any defects, inconsistencies, or faults in the raw materials, components, and finished products. These techniques may include visual inspection, dimensional inspection, non-destructive testing, NDT, and functional testing.
The pouring of an iron casting at the Pilsen Steel Foundry is a mesmerizing and complex process that showcases the pinnacle of precision and teamwork in the world of metallurgy. The foundry, with its state-of-the-art facilities and highly skilled team, orchestrates this procedure with remarkable finesse. The process begins with the preparation of the iron, which is heated to its molten state in a massive furnace. The fiery glow of the furnace, illuminating the foundry like a miniature sun, is both awe-inspiring and a testament to the intense heat required. As the iron reaches its liquid state, it undergoes careful quality checks to ensure it meets the exacting specifications required for the casting. The team at Pilsen Steel, well coordinated and attired in protective gear, takes their positions around the pouring area. The casting mold, intricately designed and meticulously crafted, is set in place with remarkable precision. When the molten iron reaches the ideal temperature and quality, it's time for the awe-inspiring moment of pouring. The crane, operated with utmost precision, lifts the crucible containing the molten iron and slowly positions it over the casting mold. As the crucible tilts, a fiery stream of liquid metal cascades down into the mold. The sight and sound are breathtaking, resembling a volcanic eruption on a smaller scale. The entire process is a harmonious dance of man and machine, where every movement is perfectly timed and synchronized. The expertise of the Pilsen Steel team ensures that the iron flows smoothly into the mold, filling every intricate detail. Any mistake or deviation could result in a flawed casting, making the teamwork and precision involved even more crucial.
The production of OSCA machinists' hammers is a fine example of precision engineering and craftsmanship. The manufacturing process begins with the selection of high-quality materials, including electro-inductive hardened steel C45 for the head and a patented 3-component handle. Once the steel has been electro-inductively hardened, it is forged into the shape of a hammerhead. Forging involves heating the steel to a high temperature and then shaping it using a series of dies and hammers. This process helps to create a strong, uniform grain structure in the steel, which further enhances its durability and wear resistance. After the hammerhead has been forged, it is subjected to a series of grinding and smoothing processes to create a smooth, uniform surface. The hammerhead is then lacquered to protect it from rust and corrosion. The striking faces and blunted edges of the hammerhead are polished to a mirror-like finish using a series of grinding and polishing wheels. This creates a smooth, flat surface that is ideal for striking metal surfaces without leaving marks or dents. In the production of OSCA machinists' hammers, robots are used in the manufacturing process to ensure precision and consistency. The robots are programmed to perform a series of tasks, such as forging, grinding, smoothing, and polishing, with a high degree of accuracy and efficiency. This helps to ensure that each hammer produced is of the same high quality and meets the strict standards set by the company. The patented 3-component handle is made of a nylon outer layer, an anti-slip rubber grip, and an aluminum alloy core. This unique design helps to reduce vibration and makes it easier to grip and hold the hammer during use. The handle is also designed to be comfortable to hold, reducing the risk of hand fatigue during prolonged use. The head of the hammer is mechanically fixed to the handle using a steel wedge and red epoxy resin. This ensures that the head is securely attached to the handle, reducing the risk of the head coming loose during use. Once the hammers are manufactured, they are subjected to rigorous quality control procedures to ensure that they meet the high standards set by the company. This includes testing the hammers for durability, safety, and reliability.
Collaborative robots, cobots, have significantly impacted the welding industry by automating processes that were previously labor-intensive and potentially hazardous. When used to automate the welding process, cobots bring several innovative features and functionalities into play. Sensor technology. Cobots are equipped with sensors that enable them to detect the position and orientation of workpieces with precision. In welding applications, these sensors allow cobots to accurately locate the weld seam and adjust their movements accordingly. Welding tools integration. Cobots can be equipped with welding tools, such as MIG, metal inert gas, or TIG, tungsten inert gas, welding torches, that are specifically designed for robotic welding applications. These tools are mounted on the cobot's end effector and controlled with precision to perform the welding process. Real-time monitoring. Cobots utilize vision systems and other sensing technologies to monitor the welding process in real time. They can detect variations in the welding environment, such as changes in material thickness or joint misalignment, and make adjustments to ensure consistent weld quality. Collaborative operation. While cobots are capable of autonomous operation, they can also work collaboratively with human welders. Cobots can handle repetitive tasks, such as tack welding or seam tracking, while human operators focus on more skilled aspects of the welding process, such as joint preparation or quality inspection. Safety features. Safety is paramount in welding applications, especially when humans are working alongside robots. Cobots incorporate safety features such as collision detection, speed and force limitation, and safety-rated software to ensure the well-being of human operators. The Yaskawa Arc World Dual Robot Welder operates on the principle of coordinated motion between two robotic arms, amplifying both speed and precision in welding tasks. These robotic welding systems are pre-engineered and pre-assembled, arriving ready to weld, thus offering a flexible and cost-effective solution for integrating robotics into welding processes. The Arc World work cells can be configured with multiple robots, heavy-duty positioners, or servo-controlled external axes to facilitate synchronized movement. This enables them to handle large parts and heavy deposition welding efficiently. With the capability to manage parts up to 5 meters in size and payloads up to 6,300 kilograms, the Arc World work cells are particularly suited for labor-intensive tasks involving substantial components. One of the key features of Arc World is its ease of integration. Despite their size and power, these work cells are designed for straightforward setup and relocation, arriving pre-assembled on a common base. Moreover, they are modular and scalable, allowing for easy expansion of productivity without requiring additional space. From single stations to dual robot configurations, the Arc World system adapts seamlessly to changing production demands, ensuring enhanced efficiency in welding operations. The integration of robot welding technology into the production of aluminum tanks signifies a pivotal advancement in manufacturing efficiency and precision. Traditionally, semi-automatic welding processes required manual intervention, limiting productivity and consistency. However, the adoption of robot welding systems heralds a transformative shift, enabling companies to meet evolving market demands with unparalleled efficiency. Previously, aluminum tank production relied on manual semi-automatic tacking operations, which, while functional, lacked the precision and speed necessary to remain competitive. Recognizing the imperative for improvement, companies have turned to robot welding systems to revolutionize their manufacturing processes. These robot systems typically feature multiple workstations, allowing for continuous operation without downtime. While the robot performs welding tasks at one station, personnel can load and unload materials at another, ensuring optimal utilization of available production time. Despite the initial investment required for implementation, the benefits of robot welding technology are manifold. Companies experience significant cost savings, with machine hours per seam reduced by up to 50%. This increased productivity and flexibility not only enhance profitability but also allow for better adaptation to fluctuating production demands. Moreover, robot welding systems ensure consistent quality and precision, leading to a reduction in defects and an overall improvement in product standards. The ability of robots to operate continuously without fatigue or breaks further optimizes production output, extending working hours beyond traditional shift lengths. Importantly, the introduction of robot welding does not entail job loss but rather redefines the roles of personnel, focusing on tasks such as assembly and material handling. The uniformity and efficiency of robot operations positively impact subsequent manufacturing stages, resulting in cascading benefits throughout the production process. Early trials and acceptance tests have shown promising results, with significant reductions in cycle time observed. This rapid turnaround underscores the potential for a swift return on investment, positioning companies at the forefront of innovation in aluminum tank manufacturing. The IGM Robot Series RTE 400 represents a culmination of over 40 years of experience in the development of welding robots and the planning of production plants. This series offers a comprehensive range of system modules, with the main module being the RTE 400, renowned for its exceptional performance and versatility. At the core of the IGM robot's capabilities are its outstanding programming techniques, facilitated by both the K6 programming teach pendant and an offline teaching system. This dual programming approach provides users with flexibility and efficiency in programming, enabling seamless integration into diverse manufacturing environments. The design of the IGM robot prioritizes optimal performance, featuring a large work zone and perfect welding access to seam positions. This is achieved through an optimal axis geometry and the mounting of the welding torch in the wrist axis, which is implemented as a hollow shaft. Additionally, All cables are neatly routed inside the robot arms using hollow shafts, ensuring a tidy setup while minimizing interference. Modularity is a key aspect of the RTE 400 system, with extremely slim robotic arms that are optimized for weight and rigidity. Different arm lengths are available for axes 2 and 4, allowing users to select the appropriate range of movement for their specific applications, enhancing versatility. High-performance components are integral to the IGM robot's operation, including highly dynamic, maintenance-free AC servo motors and rigid cast aluminum joint constructions. These components ensure high rotational speed, quick acceleration on all axes, and minimal maintenance requirements, contributing to overall efficiency and reliability. Specialized for arc welding, the IGM robots feature a unique design where all welding media are directed through the main axis and then through the hollow shaft into the wrist axis. This design enables the welding torch to complete 2 full turns, enhancing accessibility to tight workpieces and circular seams, thus ensuring precise and efficient welding operations. The IGM robot's axis arrangement and integration are meticulously designed to optimize performance and functionality. Axis 1 serves not only as a drive axis but also accommodates welding media such as cooling hoses, gas hoses, cable conduit hoses, water-cooled cables for welding current connection, and control cables for wire feed. Furthermore, the wire feed is integrated into Axis 1, protected from environmental influences with a cover, maintaining a slim profile for the robot and welding equipment. Versatility is a hallmark of the IGM robot series, with options ranging from 6-axis to 8-axis welding robots, catering to various welding applications. Additionally, multi-purpose IGM robots are capable of welding, cutting, beveling, and other tasks, offering a true multitasking capability with the ability to exchange tools as needed. In various applications such as pick-and-place welding assembly and smart fabrication processes, IGM robots demonstrate their versatility and efficiency, making them an indispensable asset in modern manufacturing environments. With their advanced technology, precision engineering, and modular design, IGM robots redefine the standards for welding and fabrication automation. At LNS North America, the production process for custom conveyor manufacturing is a seamless blend of cutting-edge technology, skilled craftsmanship, and meticulous attention to detail. The process begins with the cutting of raw materials using a state-of-the-art 6K fiber optic laser. The next step involves using metal press brakes, which allows for precise bending and shaping of the components to meet the exact specifications of the design. After the bending process, the components are transferred to ergonomic welding stations, where skilled welders like Ethan Cooper meticulously join the pieces together. Their expertise ensures that each weld is strong, durable, and seamlessly integrated, laying the foundation for a reliable conveyor system. Following welding, The components undergo metal finish grinding to smooth out any rough edges and imperfections, ensuring a flawless finish. This step not only enhances the aesthetics of the conveyors but also improves their functionality and longevity. Once the components are properly finished, they proceed to mechanical assembly, where they are expertly assembled into the final conveyor system. This stage requires careful attention to detail and precision to ensure that all components fit together seamlessly and function as intended. Finally, the assembled conveyors move to the paint booth, where they receive a durable and visually appealing finish. This finishing touch not only enhances the appearance of the conveyors but also provides protection against corrosion and wear, ensuring long-term performance and reliability. Throughout the production process, collaboration, communication, and a commitment to excellence are paramount. From cutting raw materials to final assembly and finishing, every step is executed with precision and care, resulting in custom conveyor systems that meet the highest standards of quality and performance.
The video shows the process of manufacturing pistons by MS Motor Service International GmbH. The raw materials used in the process are primarily aluminum alloys. The piston mold is made from sand, which is packed around a pattern of the piston. Molten aluminum is then poured into the mold and allowed to cool and solidify. Machining. The piston is then machined to achieve the desired dimensions and surface finish. This involves cutting and shaping the piston using specialized tools such as lathes, drills, and grinders. The 100% accurate X-ray inspection is an important quality control step used in the manufacturing of pistons to ensure that the piston cooling channels are free of defects and meet the required specifications. The production lines are flexible, allowing for pistons with a diameter of 65 to 135 millimeters to be manufactured. Surface treatment. The piston is subjected to various surface treatments to improve its durability and resistance to wear and tear. The surface treatment process includes using nanofrix, a coating technology that enhances the surface quality and reduces friction. This surface treatment ensures that the piston is more durable and has a longer lifespan. Quality control. The pistons undergo rigorous quality control measures throughout the manufacturing process, including dimensional checks, hardness testing, and visual inspections.
Steel drums, also known as steel barrels or steel containers, are widely used for the storage and transportation of various materials, such as chemicals, food products, and hazardous substances. These sturdy and reliable containers are essential in industries around the world. The manufacturing process of a steel drum involves several intricate steps to ensure its durability and functionality. The selected steel sheets are cut into the desired size and shape. The dimensions of the steel sheet will determine the final size and capacity of the steel drum. Folding the edges. After cutting, the edges of the two ends of the steel sheet are folded to create a smooth, rounded edge. Rolling into a cylinder. The steel sheet is then rolled into a cylinder shape, forming the body of the steel drum. Pressing the edges. To secure the seam and create a closed cylinder, the edges of the steel plate are pressed together using specialized machinery. This process results in a tightly sealed joint that prevents any leaks or spillage. Pin insertion. After pressing, a pin is inserted through the seam to hold it securely in place. The pin ensures that the seam remains intact during the drum's use and transportation. This step adds an extra layer of security to the drum's construction. Rib creation. To reinforce the structure and add strength to the drum, ribs are created on the outer surface of the cylinder. These ribs provide rigidity and help prevent the drum from deforming or collapsing under the weight of its contents. The ribs are typically evenly spaced around the circumference of the drum. Pressing the bottom plate. The next step is to press and seal the bottom plate onto the drum's body. This plate is usually made from the same type of steel as the body and is fitted and welded into place. The pressing process ensures a tight seal, making the drum completely airtight and secure. Installing the drum closure. Depending on the intended use of the steel drum, a closure mechanism is installed at the top of the drum. Common closure types include a removable lid, bung caps, or a locking ring. These closures provide access to the drum's contents while maintaining its integrity. Quality control. Throughout the manufacturing process, quality control measures are implemented to ensure that each steel drum meets the required specifications and standards. This includes checking for any defects in the seam, ensuring the drum is leak-proof, and verifying the structural integrity of the ribs and bottom plate. Testing. Steel drums may undergo various tests, such as pressure testing, to verify their strength and resistance to leaks. This testing helps ensure the drum's reliability and safety. The integration of welding robots in the bridge fabrication process marks a significant advancement in the field, revolutionizing traditional manufacturing methods. Historically, manual welding has been the norm for bridge structures due to their complex and often custom nature. However, the advent of sophisticated robotic technology has reshaped this landscape, offering a myriad of benefits in terms of efficiency, accuracy, and productivity. One of the primary challenges in adopting welding robots for bridge fabrication lies in the variability of bridge parts. Each component tends to be unique, presenting challenges for conventional robotic programming. However, advancements in machine vision and algorithms have empowered robots to adapt to this variability without the need for extensive programming. This flexibility enables manufacturers to effectively utilize robots for custom projects and even one-of-a-kind parts, overcoming previous limitations. A case study of a bridge fabrication company highlights the transformative impact of robotic welding. Initially, the company struggled with limited robot capabilities and programming difficulties, restricting them to simple part welding. However, with the implementation of Apogee robotic cells equipped with machine vision technology, the company witnessed a remarkable transformation in their production capabilities. The utilization of 2 robots equipped with machine vision sensors, coupled with advanced software, enables seamless integration of robots into the fabrication process. These robots operate on tracks within a spacious working area, accommodating large bridge components with ease. The machine vision system scans the parts, detecting any deviations from the 3D model, and adjusts accordingly, ensuring precise and accurate welding. The efficiency gains achieved through robotic welding are substantial. The company reports a 3-fold reduction in costs and a 5-fold increase in throughput. Additionally, Savings are realized in grinding, wire, and welding gas costs. Furthermore, the system's ability to identify assembly defects before welding prevents costly rework and ensures product quality. Box column production begins with the thorough inspection of incoming materials, where each plate undergoes dimension inspection to verify its adherence to specified dimensions. Following material inspection, the plate cutting process ensues, during which precise measurements are taken and part numbers are recorded to maintain traceability throughout production. Bevels are then prepared on the edges of the plates to facilitate proper fit-up during welding. Subsequently, diaphragms are carefully fitted into the box column structure to provide additional support and reinforcement, while backing strips are inserted into joints to aid welding penetration. Assembling the three-sided box structure is the next step, preparing it for the welding processes. Manual welding secures the diaphragms in place, ensuring structural stability. Ultrasonic testing is subsequently conducted to inspect the quality of diaphragm welds, identifying any defects or discontinuities. Cover plates are then fitted onto the box column structure to enclose the assembly. The welding processes are critical steps of box column production. Gas metal arc welding, GMAW, is utilized for the root pass weld, providing strong and reliable fusion. Submerged arc welding, SAW, follows, with current and voltage settings adjusted according to approved welding procedure specifications to ensure consistent and high-quality welds. Additionally, holes are drilled in preparation for electroslag welding, ESW, enabling vertical welding of diaphragms. ESW is then employed for this purpose, ensuring efficient and robust fusion between the diaphragms and the box column structure. Quality inspection is paramount throughout the production process. Visual testing, ultrasonic testing, and dimensional checks are conducted to ensure all welds meet the required standards and specifications. Face milling is performed to achieve smooth and uniform surfaces, followed by final dimension inspection to verify adherence to specified tolerances. The fitting process ensures proper alignment and assembly of components before welding. Qualified fitters meticulously fit together the various parts of the box column structure, including plates, diaphragms, and cover plates, according to precise specifications and assembly drawings. Once the fitting process is complete, qualified welders take over to perform the welding process. Surface preparation involves the removal of rust using an automatic shot blasting machine, preparing the surface for painting. Surface roughness inspection ensures proper paint adhesion and protection, after which the box column undergoes the painting process for corrosion protection and aesthetic enhancement. Coating thickness inspection is conducted to verify compliance with specifications. Upon successful completion of all quality checks, the finished box column is prepared for delivery to the customer, ensuring that it meets the highest standards of quality and reliability. Sand casting is a versatile and widely used manufacturing process with a rich history in the production of metal parts. The process begins with sand mold design, a crucial step in ensuring precision and quality. Using patterns made from wood, metal, or plastic, sand is blended with binders and hardeners in high-speed mixers. The resulting mixture is poured into molds containing the patterns. In just minutes, the sand solidifies, allowing the separation of the mold from the pattern. Skilled teams can also create cores to establish internal passages within the casting. Once these stages are complete, the molds are sealed and prepared for the essential metal pouring phase. Sustainability is a core principle in sand casting at precision aluminum casting and engineering. The company employs a computerized reclaim system to minimize sand waste by recycling it into the production cycle. Additionally, their commitment to environmental responsibility is exemplified by adopting a low-odor urethane system for sand molds, reducing the environmental impact while maintaining high-quality standards. Sand casting remains a vital and environmentally conscious manufacturing technique in various industries. For machining, EDL has invested significantly in expanding and enhancing their CNC turning and milling capabilities. They machine castings, bar stock, and billet materials using state-of-the-art machinery, ensuring the highest quality components. They also offer conventional machining services, including jig boring, jig grinding, universal milling, and turning. Their casting services encompass aluminum, brass, and bronze, with 3 primary casting methods: sand casting, gravity die casting, and investment casting. They work with various grades of non-ferrous alloys, including aerospace-specific aluminum alloys, and provide in-house design capabilities for lost wax molds and die castings.
The manufacturing process for hex head anchor bolt involves several steps, including shearing, heading, chamfering, threading, hot dip, galvanizing, and finishing. The following is a step-by-step guide to the manufacturing process. Shearing. The round bar of steel is 1 1/4" diameter by 48 inch long, galvanized. It is cut to the required length using a Peddinghouse shear. Heading. The hex head is hot forged onto one end of the steel rod using an induction heating coil that heats the end of the rod to around 2000 degrees Fahrenheit. The national upsetter is then used to forge the heated end of the rod into a hex-shaped head. Gripper blocks clamp the round bar securely in place, while a plunger or die compresses the heated end of the rod, reshaping it into the hex head configuration. The manufacturer's logo and grade symbol are then stamped onto the head as required. Chamfering. High-speed cutting blades apply a chamfer to the ends of the bolts prior to threading. This beveled end will help facilitate easy assembly of the nut once the bolts have been threaded and galvanized. Threading. Landis threaders are used to cut 8 inches of thread onto the end of these anchor bolts. Rotating heads contain chasers that cut away steel from the round bar to produce the threads. A constant stream of cutting oil is applied to reduce friction and prevent overheating. Threads are gauged by the threading operators to ensure conformance to dimensional tolerances. Hot dip galvanizing. The bolts must be pickled prior to galvanizing. This process cleans the bolts and prepares the surface of the steel to accept the zinc. The parts are first submerged in caustic soda, which removes cutting oil and other organic materials that accumulate during the manufacturing process. The bolts are then rinsed and submerged in sulfuric acid, which removes any scale from the bolts and etches the surface of the steel. The bolts are rinsed again and then submerged in flux, which is a chemical that assists in the bonding of the zinc to the steel. After pickling, bolts are placed in racks and lowered into a 12-foot long by 4-foot wide by 7-foot deep tank of 840-degree molten zinc. The bolts remain in the zinc for between 2 to 4 minutes. When the bolts are removed from the zinc, they are spun in a high-speed centrifuge to remove excess zinc from the threads. Finishing. The bolts are cooled in quench tanks so they can be inspected and packaged as soon as they are removed from the galvanizing tank. Estwing is a family-owned company that has been manufacturing high-quality hand tools in America for over 90 years. The company's manufacturing facility is located in Rockford, Illinois, and the company takes pride in designing and producing the world's most durable, comfortable, and attractive striking and struck tools. In this video, we will focus on the manufacturing process of Estwing hand tools. The first step in the manufacturing process is forging. Estwing's hand tools are fully forged, meaning they are formed from a single piece of steel. The forging process involves heating the steel to a high temperature and then hammering it into the desired shape. This process gives Estwing's hand tools their strength and durability. After the forging process, the hand tools are heat-treated to harden the steel. This step ensures that the tools can withstand the wear and tear of heavy use. After the heat treatment process, the forged steel hand tools are ground to create a smooth and uniform surface. Grinding is a process of removing small amounts of material from the surface of the tool using abrasive wheels or belts. This process helps to refine the shape of the tool and create the desired surface finish. Once the grinding process is complete, the tools are then polished to further refine the surface and create a smooth finish. Next, the hand tools are fitted with Estwing's patented shock reduction grip. This grip provides customers with the best available grip for reducing vibrations caused by impact, and it offers the utmost in both comfort and durability. All of the company's nylon vinyl grip tools are now being made with this new material. Finally, the hand tools are tested for hardness and strength to ensure that they meet Estwing's high standards of quality. Every tool is carefully inspected to make sure it meets the company's exacting specifications.
The 3-roll variable axis plate rolling machine from Davi, known as the MAV, is a robust and versatile piece of equipment designed for bending thick plates with a thickness of up to 130 millimeters. This machine operates by taking a flat plate and expertly shaping it into a cylindrical form. The 3 rolls, driven by powerful motors, work in tandem to bend the plate with precision and efficiency. The key features of the MAV include motorized rolls for precise control, a sturdy frame that ensures stability during operation, and the ability to tilt the rolls for accurate cone bending. The machine benefits from mechanical and hydraulic symmetry, which improves the accuracy of bending and ensures even load distribution across the plate. One of the standout features of the MAV is the patented servotronic copyright system, which maintains rolls parallelism throughout the bending process. This guarantees a high level of precision in the final product. Additionally, the multi-gearbox configuration enhances ease of operation and simplifies maintenance procedures. The Servo Press TSD 1600, utilizing Schuler's Servo Direct technology, is a cutting-edge machine designed for various manufacturing applications, ranging from automotive components to household appliances like washing machines and dryers. This 1,600-ton servo press offers a substantial increase in part production, up to 50%, compared to traditional mechanical presses, thanks to its innovative features. The press operates without a traditional flywheel or clutch brake combination, making it exceptionally flexible, energy efficient, and low maintenance. It's driven directly by high torque motors, providing the necessary force for dynamic forming processes. Its highly energy efficient pendulum stroke operation allows for programmable ram strokes without mechanical stroke adjustments, leading to a higher number of strokes per minute. Furthermore, the Servo Press TSD 1600 offers extensive flexibility in production. The press enables freely programmable lifting heights and movement sequences, resulting in increased output and higher part quality. Schuler has also developed specialized software tools like the Optimizer, Smart Assist, and Optimizer Pro to optimize operations and enhance part quality. One of the key advantages is the short setup and tryout times, reducing tool training periods and maximizing production efficiency. The press can seamlessly integrate subsequent processes such as welding or lasering due to its programmable time-distance sequences and rest time provisions. Schuler offers a range of servo presses in tie rod design, with pressing forces ranging from 8,000 kilonewtons to 32,000 kilonewtons, catering to a wide spectrum of manufacturing needs.
This is an overview of the socket set factory in China. It produces a range of socket sets with various options such as metric or SAE sockets, made from carbon steel or CRV, and including ratchet wrenches, screwdrivers, and more. Socket sets are a collection of sockets, ratchets, and other tools used to tighten or loosen bolts and nuts by applying torque to them. Sockets come in a variety of sizes and shapes to accommodate different types of fasteners. To make the task of fastening more convenient, sockets are often packaged together in a set along with a driver tool, such as a manual wrench or pneumatic impact wrench. This collection of tools is called a socket set. Socket sets can vary in the sizes and shapes of sockets they include, with each set designed to meet specific fastening needs. Additionally, some socket sets may include other accessories like extensions or adapters to provide greater versatility in use.
The Versatile Compact Laser Tube 100, VCLT100, is a cutting-edge laser technology system from Mozik that operates using direct diode laser technology. Unlike traditional fiber or solid-state laser systems, this technology offers enhanced efficiency and reliability. The VCLT100 is specifically engineered to provide a cost-effective solution for processing low-volume tube and bar components with a maximum diameter of 100 mm, 4 inches, round or 3 inches square, and lengths of up to 12 feet, with an optional 24-foot extension. One of the standout features of the VCLT100 is its compact design, which allows it to have a small footprint, making it an ideal choice for space-constrained environments. In addition to tube cutting, it also has the capability to cut flat sheets up to 20 inches by 24 inches, with a maximum thickness of 1/4 inch. This versatile system delivers high-end performance while maintaining an attractive price point, making it an excellent choice for various applications in the field of laser cutting. The original equipment manufacturer, OEM, industry in India has experienced remarkable growth and transformation over the past few years, making it a significant contributor to the country's manufacturing landscape. The sector encompasses a wide range of industries, including automotive, electronics, aerospace, and more, and it has played a pivotal role in boosting India's industrial output and exports. In this section, we'll provide an overview of the OEM industry in India with specific numbers. India's OEM industry has been on an upward trajectory, with impressive figures showcasing its growth. The OEM industry in India has witnessed substantial growth, with revenues steadily increasing. In recent years, the sector has contributed significantly to the country's GDP. In 2021, the OEM industry's revenue was estimated at around 2.67 lakh Indian rupees crore, approximately 36 billion United States dollars. The OEM industry has been a key contributor to India's exports. In the fiscal year 2020-21, India's OEM exports accounted for approximately 6.5% of the country's total exports, amounting to around 90,000 crore Indian rupees, approximately 12 billion United States dollars. The industry has been a substantial source of employment, directly and indirectly, for millions of people in India. It provides jobs to engineers, technicians, assemblers, and support staff across various sectors. The Indian OEM industry has a strong presence in multiple sectors, including automotive, consumer electronics, industrial machinery, defense, and telecommunications. The automotive sector, in particular, has been a major driver of growth, with India being one of the world's largest automotive OEM hubs. One notable player in this industry is Nidhi Auto, a leading OEM for sheet metal components and assemblies. They primarily operate as a Tier 1 supplier to the home appliances and automotive OEM industry, providing high-quality products and services to renowned clients like LG, Samsung, Daikin, and Yamaha. The company has achieved an impressive annual turnover of 75 crore Indian rupees, which equates to approximately 15.4 million United States dollars.